Okay, so it is time we make a baby step towards the first imaging modality that we want to cover, which is going to be radiography, right. So we talked about or projection radiography, if that was the title we put in the contents, then it's projection radiography. So essentially what recall, right, the way we want to organize and present the content is, any modality we take, we would start with the physics of the modality and then go towards the instrumentation aspect of it, and then towards the image formation, image reconstruction, and finally talk about the image quality aspects. In that regard, the first modality we will start with X-ray based imaging, right. So projection radiography and CT, computational tomography, right, computed tomography, X-ray computed tomography. So we will start with the physics of that, right. So once we finish the physics, then we will go to cover the projection radiography first, and then we will say, when we go to CT, we will say the physics is already covered, and then proceed with the instrumentation and the image recon for CT. So clearly the physics that we are going to cover is going to be used, or we will be able to make reference to it in the first two modalities, projection radiography and CT. Also, maybe at points when we are there, I would like to clarify that some of the things that we will cover here is in principle, right, to a large extent, you can carry forward that for also the PET imaging. Okay, essentially when the photons are interacting with the tissue, right, we will say we did similar things for interaction of X-ray energy. Now when you have gamma, it's just the energy is different, and therefore these are the nuances. So pay attention to this part, right, make yourself comfortable. That way when we go to the other modalities, whatever we can carry forward from here, we will make use of it. Okay. So physics of radiography. So we'll start the overview of what we want to do is, we'll start with the basic structure of an atom, right. So these are all atom, atomic structure and ionization. In fact, we kind of use this term even in the introduction, that these are ionizing radiations, right. So these are ionizing, and then there is ultrasound and MRI where it involves no ionization. So we did use those terms. Now it is time for us to formally define what it is, what we mean by ionization. So before we do that, we will do one slide review of atomic structure, just so that you know what aspect of atomic structure we exploit, which modality comes out of it. Okay, so just for that purpose. So this is nothing there shouldn't be anything new in any of the content regarding atomic structure, protons, electrons and things like that. Okay, so in some sense atomic structure is just for it's like kind of your starters. So you get to into it, but mainly we will understand the different types of radiations, especially particulate radiations, and even within particulate radiation, for the purposes of this chapter, we will talk about electron. See, particle is what you have, we will go into it in the atom. Electron is one of the particle, right. So we'll talk about energetic electron and its interaction with the tissue. That will be the focus. And then the other one is electromagnetic radiation. In fact, electron interaction is what we will, not with respect to tissues per se. We will talk about electron interaction with the material, and then here we will again talk about the other type of radiation, which is electromagnetic radiation, and these are the important effects. So in some sense, after the first few slides, in fact when I say few slides, it will still take some time for me to cover, because I don't want to rush through. Even though you may know it, you probably are very familiar. I would like to go a little slow here, because this kind of forms a big picture understanding of the different modalities, how each one is slightly different from the other. So, all likelihood the first topic we will cover in this lecture, and the subsequent lectures, and so we will lead up till the types of radiation in this lecture, and then in the subsequent lecture we will go one after the other on this, right. So, these are all subject specific. So, we are getting into the subject specific topics. Okay. So, having said that, let us move on to the first one. First one is atomic structure and ionization. So, what do we mean by ionization? We need to define that. In order to do that, we need to start and talk about atomic structure. Of course, there is going to be radiation dosimetry that we will cover, because we talked about ionization, or we will talk about ionization, and then we already mentioned in the previous lecture about exposure to X-ray and stuff. So, there is biosafety involved, right. So, we need to understand what this radiation dosimetry. Okay. So, we will cover all of this in the physics. So, basic atomic structure. Basic atomic structure is everything that you know. So, early 20th century, whatever they imagined, right, the planetary system kind of organization, right. You have the nucleus at the center, and then there are orbits, electrons spinning around the orbits. The same model is what it is. So, that is the basic atomic structure. So, what are of interest? You have protons and neutrons at the core, right, and then you have the electrons that are spinning around. Okay. So, since this is a very known material from perhaps high school, right, typically it's not like I want to deliver this because this will be boring. You know it, so you will learn. So, let us just give yourself a challenge, right. So, I am just going to have LHS and RHS. You please connect which is what. Okay. So, take some time. So, I have an atom, I have nucleons, mass number, atomic number on the left hand side. So, since you know this from whenever, right, high school, maybe it is a good time you refresh, maybe you did not read about this after that, and you are in typical electrical engineering, mechanical engineering in your higher years, and you have not really had a chance to work with the material side of it. So, maybe you forgot. Can you refresh your memory? See how powerful your memory is, right. An atom. So, what does an atom? Oh, here is an example of an atom. So, what does an atom contain? Oh, I see protons and neutrons and electrons. Protons and neutrons are at the center. So, that is nucleus. Oh, so a nucleus and electrons. What is nucleons? Oh, nucleons. Nucleons are, I see here, right, nucleons are the constituents of nucleus. So, what do I see? Protons and neutrons, right, that is labeled. Oh, okay. So, that is what that is. So, what is your mass number? Does anything ring a bell? Oh, mass number and atomic number. Atomic number, maybe that is easier if you can recall. Oh, atomic number corresponds to maybe the number of electrons. Turns out the number of electrons and number of protons are same, because the atom is net neutral. So, maybe atomic number is the number of protons and number of electrons, and your mass number has to do with your nucleons, that is the number that are there inside. What is nucleons? Protons and neutrons are there, sum of those is your nucleons. Okay. So, just go brush, it is all reasonable. I know you know it, but just to make sure, go one more time, read about it. And the reason for that is, just from what we have covered so far and the list of contents that we will be covering for this syllabus, you already saw, okay, there is some X-rays, radiation, ionization, all that, and then there is this nuclear medicine, nuclear medicine, and then I also mentioned MRI, the nuclear magnetic resonance. So that means there is some nuclear that we are talking about. Is that same as here? Is it here also you have nuclei, right? So is it something related, right? Yes. So essentially the idea is, when you are talking about the outer electrons which we will do, right, that we will cover in the X-ray part of it. But in nuclear medicine, that exploits energy that is coming out from the center nucleus. And then nuclear magnetic resonance is the magnetic property, right, magnetic resonance property at the nucleus. So in some sense we will start with the electrons in this chapter, right, and then as you can see, if the activity is from the nucleus, so then that gives rise to some modality, and then if it is radioactivity, then that is one modality. If it is from nucleus but is not radioactivity, but it has to do with the spin property, then that gives magnetic resonance, right, exploited in magnetic resonance imaging. So you know basic structure of atom, how from there different modalities can be traced. Okay. So this is something that we covered. So what we will do now is, so much is fine, right, we need to move on with more interesting stuff. So just to complete this, define the element with a particular symbol. So it's a overbeat, right. So if you have an element, you already call it as hydrogen, carbon, etc., right. So in order to represent that, we would also use its atomic number and mass number, right. So there are several ways to denote it. So carbon 12, C12, or you can write its mass number and atomic number. So it's if you say 6, that is good enough, but anyway you can also call it as carbon, right. So there are several ways to do it, several conventions. So some of the common ones are like this. What is interesting in this is, you can recognize the atomic number and mass number, and you have a name to it, but based on the relationship between that, you can comment on something is stable nuclide or unstable nuclides. So what do we mean by stable nuclides? If the number of neutrons is approximately equal to number of protons, right, in the nucleus, if the number of positive charges, right, protons, is approximately equal to number of neutrons. Remember, the atom is net neutral, so number of electrons is on the outside, so therefore this is net neutral. So number of neutrons, if the number of neutrons is approximately equal to number of protons, you can also look at it, this relationship, right, between atomic number and mass number. So mass number is approximately 2 times the atomic number, then that is considered a stable nucleate. So this has to do with the stability of the nucleus. Unstable nucleides are called radionuclides. So if it's a radionuclide, then that atom is called radioactive atom. Why is it unstable? Because statistically it is likely to undergo a radioactive decay, right. So it is in an energy state where it is not stable. So it will give out some energy and come back to a stable state. So stable nucleus means it is going to have this proposition. Okay. So unstable nuclide, stable nucleides. So these are the states, 2 states that are there. And then if you really look at it in the second part, right, when we go to the nuclear medicine, the signal will come essentially because of this radioactivity, right. But here we are not worried about the unstable nucleus part, right, or the radionuclides. Radiography is different from radioactivity. Here we are not, the first part when we do radiography, That doesn't mean radioactivity. Radioactivity means it comes from the nucleus. Okay, instability of the nucleus. So that is a subtle difference. So radiography, we are not talking about radioactivity. Radioactivity is exploited in nuclear medicine. Okay, fine. So that means we talked about stability, instability of nucleus, but when you talk about and then we talked about the organization of electrons around the nucleus, right. So depending on, right, so there is a structure to it. So how does a electron, we saw the first structure diagram where the electrons were spinning around, right. They were orbits, it was shown in a 3D sketch. So you have number of electrons, but then the number of electrons are also organized, that orbits that you have is so organized that it is labeled as K. So you have a orbit that is closer to the nucleus, which is K, referred to as K shell, L shell and M shell and N shell and so on and so forth. And by nature what happens is the number of electrons, right, for a given atom that tries to organize such a way that it will first fill the K shell, and not only that, it can have only so many electrons in a shell, in a respective shell, so that the energy is in a low energy state. So that means there is already a number of electrons that can be in a particular shell. So the quantum states that the electrons can be, right, it is restricted. So K shell, you have maximum of 2 electrons. So this N is the shell number. So as you go away, right, outer orbits, you can have more electrons that can reside, and this is a distribution. Okay. So why is this important? This is important because left to itself, the ground state requires that each of the electron not only occupy the shell that is starting from K, right. Electrons are in the lowest orbital shells and within the lowest energy quantum state. So within a shell it is positioned so that also gives the lowest quantum state. So in some sense the atom, it is favorable for the electrons, right, to be in this shells, in these shells, right, within the influence of your nucleus, so that it can be less energy. Okay. So that is your ground state or the low energy state. Left to itself, in nature it will be organized such that it is in the low energy state. That is the take home message. So that means we need to talk about these energies. If this is low energy state, and if I want to and if I say that these electrons are attached, right, it is revolving around the nucleus, there is a positron, there is a protons at the center, and so that it is net neutral. That means there is a energy with which it is binding, right, to the nucleus. So that means we need to talk about electron binding energy. So in some sense, if we already see through and look at the fine print in our definition of ground state, right, in ground state we said the electron is so organized that it is in the lowest, the atom is in the lowest energy state or the ground state. So if it is organized like that, so the electrons are not free, it is in the orbit, right. If it is organized as that, that is your ground state. Imagine if the electron is free, what energy will it have? If the electron is free, the free electron will probably have more energy, right. Why? Because that is the idea, that is the lowest energy state. So if it is free, probably it will have higher energy. In other words, to think about it, that means I need to supply some energy to release this electron, right. So your electron binding energy in some sense is the energy that you need to overcome, you need to supply so that you can free the electron. But when you talk about electron, now the question is, oh, I have different shells, which one are you talking about? Right, I mean naturally, so you have so many electrons, you have in K shell, L shell, M shell, is the energy going to be same? You might know or intuitively you can guess the center you have positive, electrons are negative, so it is all nicely revolving around it. So if the closer you are, right, the more influence of the positive charge is going to be. The farther you are, the less. So maybe to bump the electron, remove the electron from the outer shells, I may need to supply only less energy. If I have to really remove something from the shell that is closest to the nucleus, I may need to give more energy, right? I have to spend more energy to pull it out. So that means that energy is also dependent on, so for a given atom, that energy is dependent on which electron you are talking about, right? So let us just put that together. A free electron has higher energy than when it is bound to a nucleus of an atom. It is a mere statement, but I think you should read this statement as a natural follow-up of our understanding of ground state. In the ground state, if it is a low energy state, if the electron is freed, that means it has to have high energy, right? So that means where does the energy come from, right? That means you can think about it both ways. It has high energy, so if it is bound to the, if you make it, if the electron goes, binds itself to the atom, right, reconfigures itself, then energy has to be sent out in the process so that it goes to the ground state. Or if it is in the ground state, if you give it some energy, then you can free the electron. So that will be the energy that you supply, right? So naturally you are supplying more energy to what was the ground state, so the electron is going to have a higher energy state. So free electron is going to have a higher energy than when it is bound to the nucleus. So when we talk about the binding energy, now what is this binding energy? This is the energy that you need to supply to free the electron, right? Energy required to free the electrons, that is the binding energy. So it is not the energy that it is, so in some sense it is bound to this nucleus, you have to supply an energy that is greater than this bounding energy, right? That is what is called as binding energy. So you have to supply an energy that is greater than the binding energy to free the electron, okay? So that is your binding energy, but then you look at it from their atomic orbit. So for a given atom, right, it might be easier to free the atom, free the electron from the outer orbit, right? So the binding energy is not, even for a given atom, binding energy is not same for all the electrons in the atom. It depends on the shell, right? But for practical purposes in this course, right, because we have an application in mind, so we work with the so in our scale of the energies that we are talking about, we don't really care about that detail. We will be okay with the average energy, okay. So clearly the binding energy depends on the element to which the electron is bound naturally and the shell within which it is residing in the ground state. Both are, so I mean, so if you have a larger atom, right, if you have a larger atom, then there are more number of protons in the nucleus, right. So the electrons in the K shell, for example, is going to be more attracted, right. You need to spend more energy to release that. It also depends on the shell number. So the atom and the shell number of the electron both have a role to play in the determining the binding energy. For our purpose, we will say on an average what is the binding energy for a given atom, okay. So much for binding energy, and this is a very important concept. So let's make a example. First, when we talk about energy, let's get the units out first, and then we will have some feel for what numbers are we talking about with respect to. So 1 electron volt, right, is actually very straightforward. electron volt. How do we read? When you have an electron, right, it's a energy that we are talking about. So, you have a kinetic energy. So, you have an electron. Electron is what? Oh, negatively charged, right? E minus, negatively charged. So, if you make this electron travel, right, so I have a voltage drop. Voltage drop, you have a voltage drop, and if you have a voltage drop, current flows, right. So, that means the electrons move. So, kinetic energy gained by an electron when accelerated across 1 volt potential, that is your 1 electron volt. Okay. So, 1 electron volt is so many joule. So, this is the energy that we are talking about. So, now if we define this, then all the energy that we are going to talk about, binding energy, amount of energy you need to supply, what causes ionization, all of them, when we talk about energy, you will be able to relate to this units, electron volt, right. So, 1 electron when it is accelerated over a 1 volt difference, right, what is the kinetic energy? Okay. So, that is your 1 electron volt, that is going to be your units. So, typical energies, just so that we complete, because we said it depends on the element type. So, you look at here, binding energy of typical elements, hydrogen is 13.6 electron volt, air 29, look at here, lead, tungsten, kilo electron volt. So, without much detail here, just looking at the numbers and a typical atom that we sense where it could be. So, where do you see hydrogen? Okay. We are water bodies, H2O, right. So, we have a lot of hydrogens. Look at the value, 13.6 electron volt is the binding energy required for hydrogen, right. Whereas, look at lead or tungsten, 4 kilo electron volt. Naturally, they do not have inside us, right. So, if you are talking about some energy that needs to be provided to free the electrons, to free the electron from hydrogen, I need only 13.6 electron volt, right. Whereas, if I supply that 13.6 electron volt or 15 electron volt is nothing. Lead and tungsten, it is in the kilo electron volt. Okay. So, in that sense, nothing will happen if I supply some energy 14 electron volt or 20 electron volts or 100 electron volts to a lead, nothing is going to happen. You are not going to be able to free the electrons. Whereas, hydrogen requires very small quantity, right. So, by mistake, if I supply some quantity of energy thinking I want to free the electrons in lead, but instead of lead human tissue is there, then you see the problem. So many electrons will be freed, right. Okay. So, we will talk about that in the subsequent slide as well. That is a important concept which we will now, ionization and excitation. What is ionization? Or knocking off an electron out of an atom. Now you understand, we talked about binding energy of an electron. So, that is the energy that I need to supply to free the electron. Now, what is ionization? Ionization is knocking an electron out of the atom. So, in order to do ionization, right, in order to knock an electron out of the atom, what should I do? Oh, I need to supply a energy that is greater than the binding energy. So, if I supply an energy that is greater than the binding energy, the electron will be kicked out. What happens if the electron is kicked out? Oh, if atom is neutral, I send energy and kick out the electron, then the electron is free and then the atom will become positive, right. So, you have ions are created, right. if I supply energy and knock an electron out, then I am creating ions, right, E minus, and then this one will be plus. So, I have created ions. So, the process of kicking an electron out to form an ion is ionization. So, in order to do ionization, what do you need to do? I have to supply energy that is greater than the binding energy. So, now you see the problem, right. Now you see the problem. If you do ionization, right, you are breaking the stable atom into its ions. Okay. So, what will happen immediately? So, first it creates a free electron, right, plus an ion. So, an atom with a positive charge, that is your ion, right. So, you create a free electron and then there is ion, that is why it is ionization. Okay. When does it happen? Occurs when radiated energy above the electron binding energy. So, when you hit, when radiated with energy, meaning you supply energy, you subject this atom to an energy that is greater than binding electron binding energy, only then ionization takes place, right. So, what do you mean by excitation? Oh, excitation means like excited, you put in some energy, right, then you are excited, right. You are in a ground state, dull, then you infuse some energy, you get excited, but that is not detrimental by itself, right, because so in some sense you are providing energy here also. So, you are making it go away, rise above the ground state energy level, but then it is not knocking the electron out. If it knocks the electron, it is ionization. So, excitation is knocking an electron to a higher orbit, not outside the atom, to a higher orbit. So, I am putting some energy to pull the electron out. So, from K it is coming to L, it is coming to M, right. In order to completely come out of the atom, it needs to come out of all the influence, but I did not provide that much energy. I just provided energy such that it was trying to come out from K, it was coming to M, and that is it, energy is expanded. Then what happens is, from the ground state, it is now in an excited state, meaning the electrons is occupying the higher orbit. So, left to itself, what it will do? So, when the radiation is lower than the binding energy, you just excite, you do not kick it out of the atom, or you do not knock it out of the atom. So, either case, if you look at it, nature has it that it has come to ground state. Okay. So, how does it come to ground state? So, now you have supplied energy. So, now you have a high energy state, both the free electron and the ion in the higher energy state, because you supplied some energy. So, immediately what will happen is, the electrons will try to come form the ground state for the atom. Likewise, if it was kicked up to outer orbit, right, in case of excitation, it will now come back to its lower orbit state, lower energy state. In the process, it will send out the excess energy. Okay. After either ionization or excitation, an atom has higher energy, right. Now, immediately what it will do? It will try to come back to ground state. Okay. So, diagrammatically representing that, this is your atom, you send some energy. So, it is called as radiation here, right, we will come to that. So, you have radiated with energy is what, so it is radiation. So, you are supplying energy. So, the energy that you supply, if you have enough energy that is greater than your binding energy, then it kicks out the free electron. So, you have a hole. So, same thing, if it does not kick out the electron in the outside the atom, but if it kicks it into higher orbits, then also you will have a hole. So, either excitation or ionization, you essentially have higher energy state and there is a hole that is created because of the electron that is left out or moved out of that shell. So, now immediately what will happen is, it cannot stay in that high energy state, it has to come back to ground state, right. So, that means it has to, it is now excited, it has all the energy, it went up, it has to lose all the energy to come back to ground state, or because it has to come to the ground state, that is the nature's order. In the process of coming to the ground state, it has to shed the extra energy, right, send out the extra energy. So, returns to ground state by rearrangement of electrons. Why rearrangement? Right, we talked about when it comes to ground state, it so chooses its alignment, it comes to the shell, and even within a shell it takes a quantum state, that is the lowest configuration that it can, and therefore, that is rearrangement. So, causes the atom to give off energy, yeah, it has to give off the energy because that is excess energy. So, when this energy that is given off, right, it is called as characteristic radiation. And why it is characteristic? Because the energy that comes out is characteristic of, so these are all energy. If you look at your spectrum that we saw in the introduction class, right, you had infrared, light, X-rays, visible light, X-rays, gamma rays, right, all of them are based on energy. So, we had wavelength, energy axis, remember frequency axis, we had all the three there. So, essentially if you give the energy out, and if that energy comes out in one of these, that is we call as the characteristic radiation. It is characteristic of the energy gap that it is coming, that is making this excess energy come out in this particular wavelengths. Okay. So, that is your characteristic radiation. So, now let us for example, right, take a case to just get a feel for a number. You have an electron that is accelerated through a X-ray tube where the anode is made of tungsten. Okay. So, when I say electron is accelerated, that means I have voltage drop, and recall your definition for electron volt. If one electron, right, is accelerated across a 1 volt potential difference, the kinetic energy acquired is your electron volt, remember. So, here it is not 1 volt, it is 120 kilovolts. So, when I have an electron that is accelerated through X-ray tube, right, where the anode material is given as tungsten, and the potential difference is 120 kilovolts, right. So, what is the maximum number of tungsten atoms that can be ionized? So, now in some sense we are putting all the terminologies together. So, if I have to answer this question, if you have to answer this question, what do you need to know? Oh, binding energy. I need to know the energy that is there, that is hitting this tungsten, the kinetic energy that is hitting the tungsten. So, we say energy that is needed, and then that energy is obtained from as the kinetic energy of this electron dropped across 120 kilovolts, and then what is asked? Ionization of tungsten atom. So, then you will have to know something about the tungsten atoms characteristic, right. What is that? Binding energy. So, if you know the binding energy of the tungsten, then you can quickly calculate and say, oh, I know the energy that is being supplied to the tungsten, right, because it is one electron accelerated across volt, 1 volt is the kinetic energy is 1 electron volt. Now, it is 120 kilovolts. So, it is 120 kilo electron volt is the energy. That is what the tungsten atom is bombarded with, that is what it is radiated with. Now, if we know the tungsten's binding energy, that is the average binding energy of tungsten atom, then I can calculate for one electron, right, one electron to leave, one atom to be ionized, I need so much binding energy. If I hit with 120 kilo electron volt, how many atoms can be ionized, right, simple. So, the electron will be 120 kilo electron volt kinetic energy when it is heating the anode, when it is reaching the anode. So, anode you have tungsten. So, the average binding energy of tungsten is 4 kilo electron volt, which is what we saw in a couple of slides ago, right. So, if this is there, then you can immediately calculate the number of atoms that can be ionized, right, 120 by 4, because it is kilo electron volt and right the K gets cancelled. So, you have 30 atoms. So, you get the feel for what ionization is, what energy level are you talking about. Remember what is the, so for our purpose what is, so this is fine, right. Is this too much or too little? Okay, 30 atoms are ionized, right, hitting 120 kilo electron volt. You are ionizing tungsten, you are not really worried right now. What will I be worried? What will you be worried? I want to make sure I don't ionize the body, that means in relation to hydrogen. So, we are interested in ionization of hydrogen. Okay. So, all the energy we are interested in ionization of hydrogen for all practical. So, here ionization of tungsten is explained because you have to generate X-rays, right. So, this will come in X-ray tube. Okay. So, for all practical purposes, what we will be interested in, radiation energy greater than 13.6 electron volt, we will call it ionizing radiation, because that is enough to ionize hydrogen. Okay. So, clearly what is called, what is the energy that is needed for ionization depends on the material that you are talking about. So, 13.6 electron volt cannot ionize tungsten, but it can ionize our hydrogen, which is what we are composed of, right, a lot of hydrogen. So, for our purpose, any energy that you irradiate the body with, which is greater than 13.6, which is the binding energy of hydrogen, which is ionization of, which can cause ionization of hydrogen, is ionization for us. It is, we need to call it as ionizing radiation. Clear? So, in medical imaging, we employ X-rays, right, ionizing radiations we talked about. First is X-ray based. So, X-ray energy in this range, right, 30, 40, 60, if it goes out, it can ionize so many atoms for hydrogen, right, because it is only 13.6. Here you have kilo electron. So, you can actually go thousands of atoms can be ionized. Clear? So, that is important. So, that is the radiation, ionizing radiation, when we talked about in medical imaging, when we talked about biosafety, we said radiation, in fact we will cover radiation dosimetry in the end, alright. So, when we talk about ionizing radiation with respect to human body, we are interested in ionization of hydrogen. The electron binding energy of hydrogen is 13.6. So, anything greater than this has a potential to ionize human body. Okay. So, that we will keep in mind. So, now the question is, how do you cause ionization? I mean, it's not, you don't want to cause ionization, let me not phrase it that way. How much radiation you need to give, right? How do you give? These are two aspects. So, if I want to generate in the X-ray tube example that we saw, we wanted to create ionization. Why? Because ionization itself is not an issue. After ionization, what will happen? It will try to go back to its ground state and therefore give out energy in a certain characteristic range, right. So, when the tungsten in the previous example is bombarded, so many atoms are ionized, then what will happen? Oh, it will the atoms will try to go back to its ground state, thereby it will give out energy, and that energy comes out in the X-ray range. That is why it is X-ray tube, right. So, it will give out energy, and that energy that comes out is in the X-ray range. So, in some sense you are creating X-ray energy, and in the modality what we want to do, we want to use that as a probing signal. We want to send X-ray energy through the body, right, and then make use of it, see how it interacts with the body, and so detect whatever is coming through on the other side. So in some sense we are talking about through transmission. So we are sending X-ray energy through the body, what comes out on the other side, it is through the body, through transmission. So in fact, in some sense in the gamma also that is what we do. The radio tracer is going, the energy, radioactivity energy is coming in a different range, say gamma energy, but it is essentially the energy that is coming out, but it is coming out from inside to outside, through the body it is coming, through the tissue it is coming. So in this case, in the first part, X-ray imaging, we send the X-ray, generate the X-rays outside, send it through the body and collect it outside through the, when it leaves the, exits the body, correct. So in some sense you can have two types of ionizing radiations. One is, you can, already we saw particulate. What is particulate? Oh, particles. What are the particles in atom that we were, in one example we already saw? Oh, electrons, protons, right. So how can I use a particle for ionizing radiation? Just now we saw a electron, which is a particle. If you give voltage drop, it gains kinetic energy, bombards on tungsten, ionizes it, and once after ionization, when it gets back, the atom tries to go to its ground state, it releases X-ray energy. So you can create ionization using particulate, or you can use electromagnetic radiation. So there are two types of radiations. Here again you will notice what is an example of electromagnetic radiation? I kind of said it. So what happens in the X-ray tube? We said after the X-rays are generated, that X-ray has to go through the body. That X-ray is just a energy, right? X-ray energy, it's energy packets. So it's electromagnetic radiation. So the electromagnetic radiation is sent through the body, and that energy, if again is greater than your binding energy of your hydrogens, we call it ionizing. So you can cause ionization by two types of radiations. One is particulate, the other is electromagnetic. Particulate will be exploited in the instrument to generate a source of energy, whereas electromagnetic radiation is going to interact with your tissue or cause radiation, ionizing radiation, right. It is going to cause ionization through the tissue. Okay. So particulate is any particle, proton, neutron or electron, if it possesses enough kinetic energy, that is what it is. Okay. So, so yes, you can actually also create a charged particle and direct that particle through your body, right. You can do that, but typically in the example that we saw, we already saw that particulate radiation was exploited in the X-ray tube. So kinetic energy, what is the kinetic energy? Kinetic energy is due to the motion, right. It came, so it has a mass and it is moving. So you can, in some sense we will have to talk about the mass of the moving particle. Mostly we do not take consider to speed of light, right. The velocity is very negligible, then the relativity theory does not mean much. Whereas these particles, electrons or photons, can be actually moving at a velocity that are fractions of c. Okay, and therefore we will have to get the mass not just as a rest mass, but because of the velocity it has a relative mass. So mass of this moving particle is m naught, which is the rest state of the mass, but it is accelerated, right, it moves with a velocity v, which is a reasonable fraction of c. Then we will have to use m, the rest mass. So if the velocity increases, the mass also increases, right. The velocity is 0 or very insignificant compared to c, then m is equal to m naught, that is your rest mass. Okay. So why is mass important? Because energy and mass are related by E is equal to mc square. Clear? So this is the energy, we are interested in the kinetic energy. So what is kinetic energy? Kinetic energy is, you have rest state some energy, because of velocity you are moving, acceleration, you have some other energy. So the kinetic energy is the difference between these two. right. So, kinetic energy is E minus E naught. So, quickly you can substitute E is equal to mc square. So, m minus m naught c square. If V is negligible, then it comes down to your typical Ke, which is half mv square or half m naught v square. Okay. So, that is your particulate radiation. So, we will actually stop here. We will continue forward because we have now covered the two types of radiations, and we started with what is particulate and where does it get the energy. What we need to still do is understand what are the typical interactions of this radiation with the material. Likewise, then we will introduce electromagnetic radiation and what are the types of interaction of this electromagnetic radiation with the material. If we cover that, that is a huge step of the underlying, remember underlying what? In X-ray projection radiography or X-ray CT, we are interested in catching the attenuation property of the tissue to the X-ray energy. So, if we cover the what do we mean by these and how ionizing radiation and how does it interact, if we cover that, we are getting our clues as to what our potential signal is, right. So, we will stop here, we will continue forward with this material in the next lecture. Thank you.